be a delay timer on YouTube, but basically I can start my timer already. So we said we're gonna start at 5 o'clock. So I am actually just going to jump a little bit. So we have 8 minutes left. Here we go. And I'm gonna stop you sharing. Yeah, sorry, let me mute myself on YouTube.
So
I'm
your
gonna stop.
video gonna be a timer?
Yes, I'm gonna, you will have to screen share again later. I'm gonna stop you from screen sharing and share mine, okay?
All right.
Yeah, so, and I am going to share this one.
Yeah,
so
while I'm doing the introduction, you can start the screen sharing.
Exactly,
Okay.
that's how we will do it. But I do need to also get my...
Man, you're a well-oiled machine.
Yeah, we've done it quite a few times now. Right, where is the... I need to start broadcasting. Broadcast, okay. So I think we now started broadcasting. Participants, we should be able to see attendees coming in, which we don't see. Okay, here we go. So we start having people coming in now. Okay. And I also need to start recording on this computer. Okay, all set. So I'm gonna mute everyone. Sorry.
Let me know the YouTube channel.
Oh, sure. Yeah, I'm gonna send you the link now. All right. Thanks. Okay, so you have the link now.
See you soon.
Yeah, I'm gonna mute everyone and let's come back in about 6 minutes. Yeah?
Yeah. Sure, no problem.
Okay, cool.
Enjoy your 6 minutes. Mm-hmm.
Okay, so I'm just going to unmute everyone. I'm going to stop sharing the screen as well. So here we are.
Hello. Good morning, good afternoon, good evening, wherever you are. I'm Mel Slater. I'm in Barcelona. Behind the scenes is Sylvia Pan, who's in London, and I'm very pleased to welcome Dr. Eyal Ofek, who's in Redmond near Seattle in the US. So today I'm very pleased to welcome the talk of Eyal, who is a principal researcher at Microsoft Lab in Redmond. He works in XR, in particular Haptics, which we'll hear about today, but also various other aspects such as computer vision for HCI and camera-based interaction. So it's interesting that he's followed a very unique path to arrive at this area. He obtained his PhD from the Hebrew University of Jerusalem, and then he founded some companies, including one called Zcam, which developed the world's first time-of-flight video camera, and that eventually led to the HoloLens. He also worked in a large corporation as head of research for Bing Maps and Mobile, developing new services and interactions, including the first street-side map service. So he's a senior researcher, as I said, at Microsoft Research in these areas. He's got a large number of papers with around 10,000 citations and has contributed substantially to the field of XR. So it's my pleasure to introduce Eyal, and I now turn over to him.
Thank you, Mel. Hi, I hope everybody can see my screen and everybody is safe.
We don't see your screen yet.
You don't see my screen. Wow.
Nope.
Okay.
Sorry. Yeah.
So let me try and
at
find
the bottom
that
there is the share screen.
Okay.
Yeah. And you have to press share.
Sharing.
Yeah.
Awesome.
Okay, cool.
And also one thing that I wanted was just to see video panel. Yes. Awesome. Okay. So, and I hope this will vanishes in. Okay. So now everybody can see my screen?
Yeah.
Awesome. All right. So today I'm going to talk about the use of haptics for virtual reality. And as Mel said, I think I got a bit of a unique way of getting there. But on the other hand, if I look back at my way, it seems like I hovered a lot around haptics, but never touched it until several years ago. And I did my PhD in vision and graphics. And right after my PhD, I didn't thought of going for a research career. I went out to start startup companies, mostly in graphics, but the last one was one where we developed a depth camera, a time of flight color and depth camera, which was the first at the time. It was 96. And it took it about 15 years until it found itself into the front of the HoloLens as its depth sensor, but it was quite a ride on the way there. I joined Microsoft in 2004. I worked at different places. The main one was I was head of research for Bing Maps and Mobile, which was at the beginning was called Virtual Earth. And the idea was to build up a representation of everything around us. And we did things from reconstruction and building models from aerial views and ground views and fitting users' photos and coming out with information from signs and text in the world. And one of those things was the world's first street side service, which allowed you to drive the streets and see in 360 views around you. And even at that time, it was clear that the real use for that will be an immersive head-up display like an AR glasses on the street, but that was way too early for consumers' AR glasses. And then I start working on AR and VR, and my interest is how to extend those applications to real life interfaces. When I mean real life, I mean going out from the virtual reality small room, or not using a single application for, say, fixing an appliance, but having an applications both in VR and AR that follows you for the entire day and change as a result of the environment around you. If people are joining in, if there is actions, it should react to that. And here I brought two examples. One was Flare, that was aimed at adapting narrative-based augmented reality applications such as game to different environments, and each person in its own room or its own apartment will see a different view of the game, but it will be playable and give the same experience. On the right is a latest work called Dreamwalker, where people go out and walk in a building or outside wearing VR. They basically are blind to their environment, but the VR world that they see is reacting to what's happening around them. So to keep them safe, to let them use resources from the real world while they're not in the small room. And when I'm talking about resources, many times it's also haptics. So when I start talking about haptics, it's obviously not my work alone. I work with a group at the Redmond, which includes people such as Mike Sinclair on hardware, and Mar Gonzalez-Franco, which came from a background of perception, Andy Wilson, which is has a large background in augmented reality and virtual reality, Christian Holz, which now is a professor in ETH, and Benko, which now is a director at Facebook Reality Lab. So why VR and AR? When I went there, I was very excited because, as I see it, it's a way to modify our senses. It's we put a computer that is between our senses and the world, and let us change what we actually sense of the world, which is everything that we know. So if we look at our senses, things such as graphics, they really emerge in the past 20 years. And frankly, what you see right now is RTX demo of, from NVIDIA that shows ray tracing. And that level of realism wasn't there even 3 years ago. Graphics. So we really are almost getting there to see graphics that are, yet we can see that they're artificial, but they're almost as our obviously restore resolution and I'm going for headsets, but it's quite good. Audio-wise, we now progressing to do real-time simulation of the dispersion of audio energy in different environments, so it will sound more realistically. We can even use 3D audio to help blind people navigate in the environment. And I believe that Mar in her talk will talk about this application of soundscape. What about haptics? So haptics, on one hand, is very natural and one of the, maybe the first sense that we actually use when we're born. But trying to render it is very difficult. First, in contrast to vision, where it's just photons that hit our retina, or audio, which is vibrations that hit our ears, then haptic is very, has a lot of variance in it. It could be force on our skin, both orthogonal, like resistance of an object, as well as parallel to the skin, like shearing. And it could change with the material, the texture of the object, how hot or cold it is, humid, and more. How can we possibly render all that? And to make things worse, most of our senses are based in our head. And probably we can use the head-mounted display to render them. But touch is spread over our skin, which is the largest organ in our body. And just to service that tangible sensation, we need to engulf the entire body. Also, while sight, audio, smell, they all give us a full remote sensing of the landscape around us. We hear everything, we see everything, we smell everything. While haptics is different. We just sample it with our hand. We don't feel the shape or of everything around us, which is a minus and a plus, because we can focus on rendering only, say, on our hands that touch objects. So much of past work was focusing on rendering haptics to the hand, and the works that I will present here are the same. So about 2 years ago, a work that started by Christopher Berger and Mar was find that haptics rendering has its limitation. It's not that necessarily increasing in quality of rendering necessarily means increasing in the feeling of the user. And when I mention uncanny valley, this is a phenomenon that was discovered in vision, where rendering people, the more accurate we rendered people, we saw that at some point there's a degrade in the satisfaction of users. And the result was it becoming, because it was becoming more realistic, but not the same level of realism in all our senses or all the parameters. It could be that they look very good, but the motion was a bit more primitive, and the result generated a repulsion sense. So in haptics, this basically means that if we are not giving a consistent rendering of the haptics, or the haptics are becoming good, but they're not supported by equivalent graphics, or vice versa, we might see a gradual increase of immersiveness and quality, and suddenly there's a drop because of an uncanny valley effect. So we need to be careful about what we actually rendering and what's not, and I will discuss that later. So what's the current haptics that people can find? Unfortunately, right now, very, very primitive. What we, if we buy a controller for VR or a controller for consoles, what we mostly see in them is something like a small vibrator or a motor that rotates a non-symmetric weight, or for some, it's still a minute amount. We can even see a small speaker, a voice coil actuator, that basically they give us vibration, what we call a vibrotactile signal. And that's maybe something that is already helping a lot for feeling of actions in games, but is very, very limited. And we wanted to extend this range of rendering. So when I'm talking about different haptics rendering, I will use different axes to discuss that. One of them is passive and active. Active device is a device that has a motor, that has an energy that needs to be supplied to that and do some action that we feel. Passive is just a passive inanimate object that we could feel its shape, but it doesn't move, it doesn't do any actions. Grounded and mobile. Haptics many times start with grounded, which means a device which has a position in the space, and we need to come to it to touch it. It could be an inanimated object. It could be a robot arm that moves around. In any case, it limits our position. We cannot go further away from that device because we will lose our haptic sensation. While mobile devices, either handheld or wearable, we can take with us. And finally, object and hand. We can have a device that tries to render an object that we pick up, or we can have a device that tries to render our body. For example, gloves. Haptic gloves are put on our body, and in order just not to interfere with our motions, they have to give the full flexibility of all our joints. And if we want to generate, for example, pressure on the object, we need to, on the hand, we need to render that over the whole hand. So hand rendering tend to be more complex and expensive. And rendering objects, for example, if I want to hold a cube or a ball, I just need to render the ball. So on the other hand, there's a large variation of those objects. So there's a trade-off between rendering the object or the hand. So let me start showing different works that were done for the haptics, and most of them are works that we did. This is by no means an exhaustive look at everything that was done, and I'm just using our works for several reasons. One is to, I hope to give you an insight to our thinking. What were we trying to do, what we got, and what did we did as a result. So let's start with how we started, and we started with passive haptic. So passive haptic is an attractive concept. Instead of having motors or complex robots that generates haptics, you can just pick up an object which somewhat resembles what you need to have. For example, in this work from Annexing Reality, they use a plate as a proxy for a wheel. Or you could have some cylindric object as a proxy for a flashlight or a sword, and so on. The main problem is, as these are inanimated objects, you need that there will be in your arm reach. So you need to know what you will need beforehand for the application, and also the application need to be to know where the objects are, and I hope it could leverage on bringing the objects to being the virtual object to where the real object, because not necessarily those proxies are in the correct position. So we like that, but we wanted to enhance that, and we did that by using redirection of the hands. And this was shown in a work called haptic retargeting. So what is haptic retargeting? Suppose I have a single cube on a table, and however, I want to render much more complex object. For example, I want to build a castle in Minecraft, and I might need 200 cubes to put one on top of the other, but I only have one cube on the table. So how can I do that? Let's look on the left. There is a green cube on the table, and I want to right now simulate another one, say the red cube next to it. It doesn't exist, but the user see it in his virtual reality headset, and as he wants to pick it up, he move his hand closer to that cube. And as he moves his hand closer to the cube, we actually show him his hand in the wrong position. We actually take his hand and move it ever so slightly away from the real cube into So the user sees that and tries to compensate for this motion by moving his hand in the opposite direction. And as he does that, he's gradually getting closer and closer to the real cube, so that exactly at the moment where his virtual hand is touching the virtual object, his real hand is touching the real cube. Now, this is a very, very strong effect. We show it to hundreds of people, and those people saw the effect beforehand, so they knew that they were about to be fooled by the system, and still it does work. People are surprised to find the real cube in a new position. And we can do even more. We could warp the world as you do that to give a sense as if you putting one cube on top of the other. I'll let Maddie describe that.
We conducted a user study to gauge immersion levels associated with each approach. This minigame uses haptic retargeting to provide the illusion of arranging and stacking different cubes in the virtual environment. As the instruction billboard guides you, each time you place a cube in the correct location, with the press of a button, it will solidify. Then, a new cube will spawn to continue the rearrangement. Though it appears you're reaching for a new cube, you're actually moving the same one. Participants reported higher presence levels from the hybrid approach in comparison to each warp used individually, and overall preferred haptic retargeting over the virtual wands method. With spatial warping, in addition to spawning new cubes, we can also provide the illusion of stacking. This is done by applying a height warp as the cube is moved around. This close-up shows how the user feels haptic feedback from the table, convincing the user that the bottom virtual cube actually exists. With our system, haptics can be repurposed for a richer immersive experience.
Okay. Going based on this work, we wanted to make it more general. First, we wanted to do things more than cube. We wanted to answer basically as much games and experiences that we can have. So this led to the work of a sparse haptic proxy. So what we did here is we used the wall as a general haptic proxy. What you see in the image is a curved arm reach for all direction, but we could have just used a flat wall standing in front of a flat wall. Second, we use the eye gaze and hand motion to predict where a user is about to touch. And then as they do that, we're generating a redirection on the fly. And it could be that the user is looking at one target, and as he moves his hand, his gaze go to another target, and he locks on it, and we update the redirection on the fly. So here's an example of using it for applications such as a detective that comes to the room and try to find out who. So he can touch different objects, and although he touches this curved wall, the objects are not necessarily on that wall. And the timing is operations, so whenever you touch something, you feel resistance. Since most of the touching was unfair, there wasn't much normal duration. Versus unless
Sorry, can I interrupt here? The computer audio is very loud, so we can't actually hear what you say. Yeah, sorry.
So let me say it again. Actually, I put there in. This was designed so we can do multiple experiences. So, for example, you saw a game where someone goes into a room and touch different objects. And the objects are not lying on the wall. They could be closer, they could be further away, and the redirection takes care of that. What we did notice was, since the interaction was touching with the tip of one finger, we designed the wall to have a wide variety of plane normals, but it didn't mean a lot when you touch with one finger. Beside one example where you are sliding your finger on the safe there, which was mapped to a plane which has a similar normal. Now, the same setup could be used for totally different games. For example, you can see here a spaceship where it has different buttons. Not all of them has normals which are similar to the wall, but it worked just as well. So it's we think it's a start of a general way to use passive haptic, which is not aimed at one specific experience. But as happy as we are with redirection and passive, it has its limitation. It's passive. It cannot generate forces on active forces on us. We have to, it just resists our forces. So we looked at ways to go for active devices, and we focused on controllers, handheld controllers. And why is that? One, it is easy to take it up from a desk and return it. And this is important for a consumer device where I might be playing and then there's a ring in the door and I just put it down and go answer it. Also, I didn't write it here, but in our current environment, it's if I'm thinking of gloves, first putting them on and taking off, it takes longer, but also controls are easy to clean between users. And it's limited, it's small, it has to be able to take it with us. It probably can render more objects that are handheld. Since it's external to the hand and the hand just goes around it, it's easier to make one controller that will fit a large variety of hand sizes, again, in contrast to a glove. And finally, if we look at current consumer VR systems, many of them already has some controllers, A for tracking, B for control, such as joysticks, buttons, and so on. It could be the natural place to put a haptic rendering. So here's the first controller that we tried to build. We didn't know how much information we need to render. So the idea was to render a normal of a plane that you touch with your index finger.
Our first device, called Normal Touch, haptically renders object surfaces and provides force feedback using a tiltable and extrudable platform. You can see how Normal Touch keeps your finger tracing the surface even if your hand movement is not very steady. Our Normal Touch device senses the finger force and can render force feedback, allowing the user to interact with deformable objects and feel their different surface stiffness.
From above.
Or a person can interact with a rigid body physics simulation. Notice how you can use the force sensing to flick the ball around.
Great. So this device basically let us feel if we touch something that there is a surface there and the normal to the surface. Is that enough? We didn't know. So we went in parallel with a different approach, which is sort of a small shape display, which is under your tip of your finger. and render the world under the finger in a 4x4 resolution.
Our second device, called Texture Touch, features a 4x4 matrix of actuated pins underneath the fingertip that individually render the 3D shape of virtual objects, including some structure of the surface texture. By moving our devices around while keeping the finger on the actuated platform, users obtain the sensation of a much larger 3D shape by integrating output sensations over time.
Great. So which one is better? Surprising, they're quite equal from preference of people and the accuracy that they were able to do tasks such as tracing details on objects. Normal touch has a better way of rendering large planar surfaces or smooth surfaces in general. And texture touch is great for small details such as a trench or a perturbation from the surface. But both can do that because you integrate the information as you move your hand. So normal touch can show a perturbation by moving around it, while texture touch can also smooth a bit its rendering, and it could render a tilted plane just as well. And there wasn't a major difference from the users. There is a major difference from complexity, number of motors, cost, and so on, which obviously made us start thinking, should we do things with less motors? Another thing which was a problem with both devices were that we tried to render grounded objects like touching a table. And while you bring the finger, it feels that the table is there. Nothing stops your hand from continue moving in and penetrate into the table. So one way to overcome that was to compensate visually for that penetration. So if my finger touches the table at the beginning, if I'm rendering it right now with normal touch, the normal touch is totally is set to 0 elevation. And as my finger tries to get into the table by pushing the controller in, the plate of the normal touch goes up and physically keep the tip of my finger outside the virtual table. And it can do that for a few centimeters, which is the dynamic range of the normal touch. Beyond that, the actual finger goes into the table, but we still render the virtual hand outside the table for about 10 centimeters, which is a range that you won't notice, which we found already for redirection. So in that year where normal touch and texture touch came out, many other devices came out, like Wolverine from Stanford, or Dexmo, which became a commercial glove. And when we see those devices, several things were getting clear. One, most of them don't leave the lab. You have motors, and even a single motor, which is working hard against your muscles. It's problematic. It requires a lot of energy, and and there's an issue of reliability. And not necessarily have more motors, they feel better in the feedback. And second, when looking at many of those devices, they were very designed for a specific application. For example, how to render weight, how to render a size of an object, and so on. And it was obvious that if we want ever those devices to come out to consumers, consumers will have to get large bang for their bucks. They need to have a device that can do a lot. So this led us to Claw. Claw is a device that can do multi-functions in one device. It could it could render as if you're holding an object in your hand. It could do touch, it could render texture. And since we were hoping that it could be eventually an actual controller, we had to put in a trigger just as well, because that's a major function of most game controllers. So let's see that.
Moving device. With Claw, you can grasp virtual objects and feel appropriate forces during grasping. You can also touch and feel the shape of a virtual object, as well as get resistance when you push on them. You can also rub virtual surfaces and feel their texture rendered underneath your fingertip. Finally, you can also feel the recoil when shooting a virtual weapon. Claw is a unique, multifunctional haptic controller that enables grasping, touching, surface texture rendering, and shooting feedback.
So, great. Is that it? Can we add more to the value? How about, right now we looked at resistance to our finger. What about friction or shearing as we move the finger on top of the surface of an object? So this one is called Haptic revolver, which is basically a cylinder that moves under the fingertip to simulate the friction with an object. And in this paper, we also use that to simulate different materials as it turns to represent, in this case, the paper, the plastic, and the table.
Our device haptically renders the scene by making contact with your finger when you touch the surface, and positioning arbitrary haptic elements in virtual space, allowing you to feel what's beneath your finger. The haptic revolver consists of a wheel that contains various haptic elements. A servo motor moves this wheel up and down as you contact a virtual surface. A DC motor spins the wheel to render shear forces and position haptic elements under the fingertip. The thumb button on the side of the controller enables input. Because our device is tracked, we can spatially register haptic elements with the environment. The motor spins the haptic wheel to ensure alignment between the features on the wheel and the virtual scene.
Great. So when we came to test that, we were getting several surprises. The first surprise that we noticed was we tried to ask people to follow a sphere and drag their fingers over a virtual surface at different speeds and different directions. And we rotated the wheel according to that speed and direction, but not always. Sometimes we actually flipped the direction and rotated in the opposite direction. So as I move my finger to the right, I will feel the surface move to the opposite direction. And here came a surprise. When we asked people how good they rate the experience of the device, we saw that it's basically symmetric. People didn't notice the direction, whether it is in the direction that they move or further away. What they did notice is when speed went down, then the quality of rendering the shearing and the friction lowers. So that got us thinking. It seems like our brain sees our hand moves. It feels the friction on the finger, and there is a discrepancy between the two, but the brain has to come out with one result. And is it just forcing us to believe that the friction is in the right direction? So if this is the case, can we use our 1D friction to render two-dimensional movement of a finger on the surface? And here came surprise number 2. We asked people to follow directions which were vertical, horizontal, or a sphere, or any path which is two-dimensional. And remember that our wheel renders only in the x direction friction. So we did several options. One was just to render shearing, which means don't start rolling the wheel, just apply a bit of force on the skin to feel the skin being tensed in the direction that you go. The second was let's roll the wheel in X and Y according to the projection of the 2D motion to the X direction. And finally is let's also render the Y speed in the X direction. Again, wrong direction. And to our surprise, what we saw is that rendering the motion in X and Y, both in the X direction, is actually quite good. And again, the brain is mapping that to the correct friction that we should feel. If we just do the projection in the X, it worked for most shape. Obviously, it didn't work for the vertical because as you go up and down vertical, projection is 0, you don't feel it. So that's why you see the green vertical line score goes down. But as we add also the Y direction in rendering of the cylinder, this start to go up just as well. Great. Can we add even more functionality on our claw? How about two-handed operation? Many devices that we use in real life uses 2 hands. But we don't want to sacrifice the way we use the controllers freely today. So we went out to see if we can add some connection between the hands that could be on one hand when we need it, feel as if it's not there, and when we need the force between the hands to make it closer to rigid. So we came out with several solutions, which we called haptic links.
Present haptic links, electromechanical connections which attach to standard VR controllers to enable intercontroller force feedback through variable stiffness actuation. In this clip, the user freely switches between dual pistols and a rifle held in both hands. Attached to their VR controllers is a haptic link. The haptic link allows for full 6 degrees of freedom motion while shooting the pistols. However, when using the rifle, the haptic link joining the controllers becomes rigidly locked, allowing the user to handle and aim the gun like a real two-handed weapon.
Okay, so as I said, we have 3 different technical solutions. The first one is really simple. It's called chains. It's like a chain of ball and socket elements, and there's a wire that goes through them. And if we pull the wire, it increases the friction between the elements and they become rigid. Beside being simple, the main advantage of such a device was that it freezes in its current position. So I could bring my hand to some position and then press a button to freeze it as rigid. So I move this and I put my hand, say, for a wheel, and now it's locked. And another press, and it's now free. We also wanted to get some level of control on what is the resistance the device makes. For example, when you use a bow, then as you increase the distance or the stretch of the string, the force that you have to apply is stronger. We couldn't do that with the chain because the chain has so many elements that has friction with them, which is really hard to control. It's mainly binary, free or rigid. So to do that, we used a layer hinge, which is like a sandwich of layers that one motor could add force on them, and by doing that, change the resistance. So as the string is being tensed, we have to apply more force. And finally, in many cases in real life, we only have a directional force. For example, if I hold a box, I cannot bring my hands closer, but I could very easily get them further away. Nothing is opposing that. Now, if I have a non-directional brake, to release my hand, I need to sense or to tell the machine that I want to release my hand. This is non-natural. So this ratchet hinge was just directional. It just stops in the direction inward. So we could simulate a box that will prevent us from getting in, but we are totally free to release it. Great. So we can do a lot of things, and we could pack them in some limited controller. So where can I buy that? And why can I don't have that in my hands right now? So we talked with different hardware manufacturers and tried to see what limits the things that we'll eventually can get as a product outside. Now, as I said, most of the product you can buy today just have a small motor inside. You never feel it in your hand. And the reason is because motors are A, expensive, B, if they need to work against our body force, they need to be strong, so they're heavy, needs more energy, and even more expensive. And finally, even those big controllers, if you leave the controller on the floor and the kids come in and stamp over the motor, you could burn the motor. So hardware manufacturers are really careful, and convincing them to come out with new technology is not an easy task. We did saw that if you use resistive brakes instead of motors, you gain several advantages. One is brakes could be very strong. They can also give up when a larger strong is applied on them without damage. They also use less power and lighter, but they also have problems. For start, they don't contain energy. So for example, if I want to compress an elastic object, then the brake will prevent me or will make it hard to go into the object, but will never render force back. Also, suppose I want to do an object that I press and it resists, and then I press more and it breaks. So suddenly there's no resistance and I can go in quickly. This is something that most brakes cannot do because they have friction, and just to release them, you need to release the force a bit and then release the brake, and then you can do it. Again, non-natural. So the next prototype that we went for is called Capstan Crunch, which is a brake-based device that also have energy storage in it. So it could represent rigid objects in my hand, but it can also represent springy object. You can see that it pushes the handle back. So how do we do that? The basic technology is very old one. Capstan is used in ships to basically multiply the user force. So when we put some force F into a rope that is wrapped around a cylinder, then the result force that we're getting by the rotation of the cylinder could be 1,000-fold. And usually the use for that is a binary device. When I put a ship or a sail, I can use fingers and it will have a force of a ton for the other side, but I can either free it or lock it. What we wanted was to have the ability to linearly change the force. So we did quite a work on finding materials that can enable us to do that. So their static friction and dynamic friction will be very, very close. So there won't be hiccups as it goes, start moving. And we end up with a device that was about to multiply the force by factor of 40, and it's directional. It stops apply force in one direction, but does not in the other. So how do we store energy? We basically use a spring, and we use another capstan as a clutch. So as we push into the object, what we feel as resistance is the spring plus whatever left force left to render is rendered by the first capstan brake. And when we release those two capstan brakes, and we just feel the force of the spring pushing out. So this is non-symmetric. We feel more force according to the elasticity of the object we press on, but going out, we feel the same. And this has already led us to do very complex profiles of haptics. For example, here is what we measured for a simulation of a push button. When we push a push button, the first finger doesn't feel anything, and then it hits the surface of the push button, and we start to feel resistance. There's a spring in it. So as we push more, the resistance grows up until some point where we hear a click, the resistance stops, the finger moves a bit and then hits a brake. So we can easily render that, as well as braking objects and things such as scissors that the force grows as you cut, and so on. And there's a surprise too. When we try to compare this brake non-symmetric device, we try to compare it to two symmetric devices. One is just holding a spring and feel the same reaction going in and out, with the caveat that it's a fixed spring constant. And we use the claw that you saw before to render with a motor that we are pressing and releasing again symmetrically. Now, when we look at the impressions of the users, we actually saw, and that was expected, that spring will be really good around its natural spring constant, but it's really bad, for example, for rendering rigid objects. And we were quite surprised to see that claw, which is a fully symmetric, was a bit lower, not a bit, it was lower for really, really low spring constant, or basically moving in free air. And the reason is our implementation. We need to move a motor and control it according to our movement of our fingers. And this has a minute delay. And you really need a very, very good control system so that user will not feel the motor as if it's air. So that's lowered the scores for claw. However, when we look at the Capstan crunch, which is a non-symmetric device, it only renders the correct compliance in the way in and not in the way out. We saw that it's quite good across the board, which made us think that actually people are more sensitive as they compress their hand on touching a new object than when they release. Another way of trying to get out of the lab and into the hands of consumers could be to have something which has no moving parts as they have today, but maybe a more rich haptic rendering. So to do that, we came out with a device called Torque, a dexterous rigid controller, which, although it's rigid, just like holding a piece of plastic, it gives the feeling that you actually compress it, and you might hold a rubber ball in your hand and feel it. it also enhanced the manipulation of objects. So if I look at a real object, when I hold it, I press it, I manipulate it, I feel how it is, maybe textures, and I could release and grab it. And we wanted to do the same with, again, a plastic rigid controller. So to do that, we can also see here a manipulation. We could move and release an object just with our movement of our fingers, not our hand. So we let the two fingers rest in a position where we put voice coil that can render vibration to those fingers. We also measure the pressure that the thumb is applying, as well as the position of the thumb. And this already let us get some functionality, such as we can rotate the object by moving the thumb on the device and moving the fingers on the other side in the opposite direction. And that is surprisingly a very good way of manipulating an object. If we compare that to the current devices where I need, in order to manipulate an object, I need to move my entire wrist and hand. And here I can just move things with the tip of my fingers. And also, we hope that the simplicity of this contraption and the fact that it's all within the controller may encourage hardware manufacturers to enrich our haptics rendering. So where do we go from here now? Let me first quote Bill Buxton, long nose of innovation. He had this paper where he looked at how different technologies went from their invention to being in a consumer product. And he saw for many of them 20 years of time to go from invention and then refinement and augmentation until you get to something that could be a product, and you get also the need goes up and it becomes a consumer product. I sure hope we don't have to wait 20 years, but it's not a slow process anyway. We do have a growth of need from the public as VR and AR will become more prevalent in the consumer market. And I would say we're right now somewhere in the middle between invention and refinement and augmentation. So there's still work on things as I showed you. Another thing is, I mentioned the uncanny valley. We want to avoid that. And the uncanny valley can happen when you touch one object and you feel it, and you touch another object and you don't feel as it should be. There's a predictability that we build up for the user, and we need to stand for it. And one way to do that, and that's the reason we went for handheld controllers, was to look at a subspace of interaction. In our case, we looked at objects that are handheld, and we can mechanically manipulate them and take them and leave them. We didn't look at temperature. We didn't look at much of texture. We also almost didn't work at grounded objects. It's mostly for things that you hold, giving more consistency when you do that. And it's also a subset that is useful for many tasks. But it's still an open research question, how we can go from rendering in the hands to manipulating walls and things around you, which we still work. And we hope that eventually we will see more such technology out to the public. So that brings me to the end. And I have no idea if I'm up to time or not. Yes, exactly.
Hello. Do you want to stop sharing your screen now?
Sure.
Great. Thank you very much. So thanks for this tour de force on, I think, the most difficult area of virtual and augmented reality, which is haptics. And before we move on to questions, I just wanted to say that when I visited your lab in Redmond, I tried out the haptic retargeting, and I think it was the most amazing haptic experience I'd ever had. It's, as you say, it's even though you know what's happening, your brain gives you this strong feeling that you were really manipulating many, many objects. So it's something really, really interesting. So there are a number of questions coming in. We'll go for questions for 10, 15 minutes, and then I'll check with you that you're still okay to carry on.
I'm okay.
Or not. Okay, so it's on the hour now. So these are questions more or less in the order that they've come. 1 second. I have to get back quite a long way. So there's a number of questions. So this is a question from, apologies for pronouncing the name, Gregor Richard, and it's in 2 parts. The first part is, regarding the uncanny valley effect, for the robotic uncanny valley, and more generally for the visual aspect in VR, there is an increased accepted reference for good visual implementation. Actually, I don't see what, and the second part is, and the uncanny valley effect triggers when you come too close to a good implementation. It's much more difficult to assess this for haptics. What's a good implementation of haptics? It could be passive, as its properties are physical and real. But in your study, if I understood it correctly, haptics were rendered through vibrotactile feedback, and the level of realism used were spatialization and or visualization. But is vibrotactile to come close to reality in terms of haptic feedback to generate an uncanny valley effect?
So what is totally right. And what we did, we looked at one aspect of that rendering, which was localization. On one hand, we could suppose right now you touching an object like a plane or a stick, and we are simulating a touch of an object which is in a location on that plane. We could just as well render the vibrotactile feedback in a way that will not generate location, very much like audio. You can have just hearing the event, or you can hear spatial audio. And now what we did, we added additional level of sensing, for example, visual or audio. Think of the following. Suppose right now you are in VR and you, I'll give an example with audio. You hear steps, but you cannot really localize those steps, and you don't see anything. That's maybe someone walking around you and so on. Or that you hear the steps, you actually can localize them. They're just in front of you and you still don't see anything. This is a discrepancy of that information. And usually what we think at that point is, oh, there's someone in the room, not in the VR, which is walking and I cannot see it. And the next thing I'll do is I'll take off the headset to see that. While before that, there was a coherence between all the senses that I served in VR. And you say, oh, someone in VR is walking in a next room or some place where I can hear it. And the same goes for haptics. If I feel where the haptics point is, and it's not back up by some visual excuse or some other excuse, then you start thinking, oh, what's actually happening there? And it doesn't have to be a very good excuse. For example, we did the following examples. We did non-localized haptic, localized haptic with non-localized visuals, localized haptic with localized visuals, and with some fuzzy visuals. What I mean is if you see a ball that jumps on the plane and you feel the position of the haptics, if the position of the haptics is not correct with where the ball is, or if you don't see the ball as you hear the knock on the plane, you start reducing immersion. If you see the ball, it's increased immersion. If you even see something like smoke around the plane, and there's maybe you move the plane, so there is some kind of possible causality for that haptics, you will maintain your immersiveness. So when we take and plot a graph between the locality of the haptics and the visual, we actually get a very, very similar graph to when you compare things such as visual fidelity and acceptance in uncanny valley. You see a growth, and then at some point there's a drop. And if you increase the rendering quality, it goes up. Again, looking at one parameter of the haptics, which was location. Obviously, we are not in haptics rendering in any way close to visual. You're muted, Mel.
There's another question which was put before the first one. Are you there? You suddenly disappeared from my screen.
Oh, I'm here.
Okay, fine. So this question is on, how can you even check if you avoided the uncanny valley of haptics? And this is from Michalis Romeliotis.
Okay. And again, this is different for the general case, or if you do a lab experiment. When you do a lab experiment, you try to control a single parameter and see satisfaction as a result of that single parameter. When you do a full experiment, what we try to do is we have a level, with questionnaires, we try to intervene and ask people. When someone is doing a very complex experiment, for example, going into a game and doing a whole environment, that's hard, because it could be that the door handle was bad and the pen was great, but maybe the door handle lowered the score. So what we try to do is just do lab experiment where there's small, very localized interactions. And again, it's mostly asking people. We don't have direct way to the brain to measure their immersiveness.
Yet.
Yeah.
David Parisi asks, I know this is a tricky question, but if Claw was designed with a consumer market in mind, what would be a target realistic price?
Wow. I'm a researcher, and I don't know how to ask that, but it's like everything, it depends on quantity. I mean, if I look at, say, devices such as coming out like the Valve Index Knuckles or things, these are quite expensive. They are around, I think, $300 to buy them. And the reason is there are a lot of components in there. And in this market, some things as cheap as 10 cents is really influential eventually. Claw, as itself, it has one motor that had to resist our forces. That motor that we bought, it was a hobbyist motor, but it cost $100. So I guess just $100 of a motor comes out to a $300 for a consumer. Usually the rule is 1 to 3. That's one of the reasons that we went to build up Capstan Claw, which gives a very good fight for the claw, but without that motor. It uses not big motor. It uses a small motor, which is, I would say, something on the order of $1. But again, I'm not buying it as a million parts. I'm buying it as one, which I think could be at the range of current devices. But that's not my expertise.
Thanks. And actually, while we're on the claw, Daniel Lobo Cuenca asks, is in the claw demos, is the hand flesh simulated as a soft body? And if so, why? Thanks.
The hand is simulated using just regular Unity model. It's not soft body. So
okay,
we just,
thanks.
Yeah.
Okay, Ewan Lavoie says, this is a great talk. Thanks for doing this. Obviously, the development of haptic technology for VR is available, but if it's slightly off, the feeling of embodiment can be lost. What do you think is the best way to measure how immersed or embodied a person feels in VR?
Very good question. Okay, there's different ways that we use. First, you're right. I mean, any cue that you give to a person in VR could become a double-edged sword if it's not at the right time or not according to expectation. And what we do is several things. One is we ask people. We tend them to rate how good is the experience, how did it fit their expectations, and we usually do that with different devices and different conditions so we can see, let them judge in perspective of other options, and do that on really small experiences that can be measured. Beside us, we try to come out with some objectives means by doing tasks. If you go in and need to touch an object and you need to stop as you feel that your finger is touching that, how good is your reaction? Or can you say which object is heavier than which? Or which one is softer than other? And you try to lower the differences between the object and see if people still feel it. And beside us, we also many times get surprised, and this is many times a good surprise, to see that we are not perfect. And we, the same way we have optical illusions, we have haptic illusions. And any haptic illusions is something that you could use either to lower the accuracy in a direction that we're not sensitive at, or to make additional illusions with it.
Thanks. Pierre, I'm switching to a couple of questions from Q&A. Pierre Giorgio says, thank you for this amazing lecture. Very interesting. I would like to ask if it could be possible maybe in the future to manipulate objects. For example, break a cube in two pieces, separate the two arms of an object like the letter U. I'm sorry. Okay, I think that's enough for the question. Thanks very much.
Okay. So yes, we did demo that we break a cube in a sense that you, and this is a combination of visual and haptics, you feel that your finger are on the cube, you start pressing the cube, and as you start pressing the cube, you also feel some vibration within the material because of the condensation of the material, you know, cracks start to forming in, and then at some point the material breaks and you lost, now you have no resistance to your fingers and they go in. And what we don't render, and so visually we have those cracked parts flying to the sides because you won't feel those hit your skin. So but giving the impression of breaking is very good.
Thanks. David Roche asks, how do you balance the power consumption required for such haptics? Consumers still want battery-powered controllers, but many of the actuators you're using require significant current.
Agreed. So so that's why we're going and using as much as possible resistive brakes, which don't use a lot of power. And whenever you do a rigid object, you can lock. So now you don't need power for that. And frankly, devices such as the Capstan are very, very efficient, and we have other. I'll give another example. We had the normal touch, the original one. We try to build up with battery and as a remote device as a demo. And basically it could work, I think something, at least 5 hours on charge. So all the time, I mean, not that in a regular use, but as a demo, we put it in an exhibition and it just move all the time, and it worked for hours. So I think we could handle quite useful controllers.
Thanks.
Power
Are you okay to carry on for a bit?
Yeah.
Okay. This is from Onyamat, and it's about handshaking rather than manipulating objects. So what are the challenges in translating such hand-to-hand object haptics to hand to remote hand? Very important these days. For example, collaboration, social VR, etc.
So I would say the first challenge, and we're talking about remote right now. So the first challenge, not just for haptics, is latency between people. We want to simulate, coordinate a operation between two people that are conversing online, and you might get this last mile problem of people standing in the corridor and one try to go left or right and you don't know which direction to simulate them. You can overcome that with retargeting of the virtual hand. You can basically, even if the hand is somewhere like this, you can just bring them together. And a haptic rendering. You could render the feeling that something went into your hand and that now generate forces of somewhat similar to handshaking. And with additional graphics, it could even be convincing. It doesn't do what it doesn't do. It doesn't usually right now, I mean, you can build a hand as a device. I didn't try that, but you don't render things such going around and pressing on your, firmly on your hand, but you will feel that some robot device came to your hand and you're shaking it. This one you could do. You could build a device that gives a more realistic handshake. My fear is that's a very, very dedicated device. It's good for that, and it will do the best for that, but is it worth it?
Thanks. Unikishrinan asks, does it make sense to adapt haptic feedback to different user physiological parameters, such as length of the fingers and disabilities? And if so, how could it be done?
Yes, of course. And okay, several things. One is I will mention a work that I didn't show here, but we have haptic devices for people with limitation. For example, we had haptic rendering white cane for people, for blind people, that enables them to walk around in virtual environment, and they can recognize the material they hit, the geometry. We have a spatial acoustics, so they could say, oh, that's behind the wall, and so on. But that was designed for people with which are blind. You can always have different levels of haptic rendering and sensing. So if people can do less motion, you could sense small emotion and render the equivalent haptic as if they did the real motion. So in order to let people feel the right experience. You can compensate for the jitter as you sense it, or you could try to even render an opposite jitter. And there was a work that was done for enabling people with jitter to write in smoother strokes, giving a pen that was rendered in, not a pen, it was a wrist that was rendered in the opposite concealing rotation. So there's a lot of opportunities there.
Thanks. William Charles, he says, thank you very much for the talk and explanation. He basically wants to know, is it possible to experience the claw anywhere other than going to you?
Yeah, that's the main problem with haptics. It's really hard to sense it from afar. It's a good question. I mean, we usually demo it in things such as conferences. I have to think of it. It's not something that's easy to right now think how you can do. I mean, maybe giving instructions how to build one, and then you can feel it yourself.
Yes, good idea. Thanks. Catherine Mimnau asks, says, thanks for the nice presentation, Dr. Ofek. Does vision always dominate when there's conflicting visual and tactile stimulation? Are there
absolutely
cases
yes.
where what is felt overrides what's seen? Yeah, very good question.
Absolutely, yes. Vision is the strongest sense. It's override audio. It's very well override haptics. It is, though, there are places that it's hard to fix with vision. For example, if the haptics comes at the wrong time, you will feel it, but your brain, if it's really close, then your brain will fuse them, and mostly the vision, I guess, will win. But if it's far, no explanation of vision, back to the uncanny valley. So we do use the fact that vision helps us a lot. For example, when we render different compliances of object, we also for sure will render different compliances in vision. And as we saw, the release was not, at least in the Capstan, was not correct, but the visual were, and people never noticed that.
Thanks. Panagiotis Cortesis, he has a couple of questions. One is, does haptic rendering basically improve task performance?
Or
the better
depends
haptic
on
rendering?
The task. Depends on the task. For getting to a target and follow a target, sometimes it does. Many times the vision, as I said, is the strongest sense, and we're already doing a very good sense with vision. But vision is less accurate in depth. Vision is less accurate when the object is underneath your fingertip and the fingertip occludes that object. Vision is obviously less useful if your hand is outside the field of view, and then you only feel the haptics. So we know that right now we're doing a lot of VR. They are without haptics, or with haptics which is only representative some major events as a buzz. And we can still do a lot of things. It's just that when you add the haptics, you feel the level of realism jump up. And at the beginning, you're surprised. Oh, I'm in VR. I didn't meant that to be real. And like many good things, once you feel them, you're getting used to them. And then you start to feel that you're missing them.
Thanks. Panagiotis also wants to know your opinion on exoskeleton devices to simulate features such as pull resistance, etc.
So exoskeleton devices are great. I mean, they're grounded. They can generate full rendering on the body, but they suffer major problems. One, they are extremely complex and expensive. Not right now, not nearly to get to the consumer market. Second, it takes some effort to get into them and out of them. Just think of gloves, which is just a part of the exoskeleton for the hands. It's maybe easy to put on one hand. How do you put on the other one? And many times it's another person that helps you with the other hand. And third, there need to be set up, many times manufactured for certain body size and proportions. So all that makes it extremely hard for non-enterprise work-specific uses.
Thanks. Mohassin Rashid asks whether people are accurate in reaching objects in VR and AR.
Yes and no. They are quite accurate in reaching, but on the other hand, if you are right now manipulating the senses, for example, you render the hands in the wrong position, they are surprisingly non-sensitive for that. So they have good hand-eye coordination and proprioception to control the muscles, to stop exactly at the right point, but it might not be the right point. And that could help us a lot in the way that we render haptics. For example, you might want to render something here, but you render it here. And for you as a VR user, this feels great, just like you wear here, because you don't feel the difference. But for us, it means that you might be closer to the device, or maybe we don't need to be as accurate where your hand is, and so on. Having said that, that might be different if we are using multiple people in the same room, because again, if you remember the handshake, you need to eventually get to an exact location. So then it's a bit different situation.
Thanks. I'm going to ask one more question from the audience and then one from me. And then I think we're finished, because I'm aware you've been on for like an hour and a half. And I think everyone knows how exhausting this can be. So Adlan Ramley says, thanks for the very insightful webinar. I have a question about the future of haptics in VR. Since controllerless hand tracking VR headsets like the Quest are becoming more popular, is there a way to integrate haptics? I'd like to see more haptics for accessibility.
So several answers to that. One is, yes, you want to have, my feeling is that you want to have both bare hands interaction as well as haptics, which will generate some kind of hardware next to your hand. For example, you might, in Quest, you might have a great navigation by gesturing with your hands, but I doubt if, for example, for a shooter game, you feel as satisfied because you really need the haptic sensation of a trigger. And we are looking at different ways that you could change between feeling of free hands and actually rendering haptics when you need it. And it's sort of a mix between passive haptics and where you have, or a encounter-based haptics when you touch an existing object, and the fact that you could take it with you. So we're looking at that right now, and but I do believe that you always want to have some haptics. Mime everything. is not as satisfying as actually feeling.
Thanks. So the last question from me is that in vision and auditory processing, it's like you said right at the beginning, is universal. So where anything that you can imagine can be rendered visually or auditorily, and you can see it or hear it in VR. So it's very general. Do you think haptics will ever reach a point where I'm walking along in a virtual environment and my elbow accidentally brushes a wall and I feel it, or my foot treads on a virtual stone and I feel it? Will it ever be as universal?
Well, I believe it. I believe that we'll get there. If I really knew how to get there, I would have done that. I do see that in places that are having larger budgets, like for example, there is a VR sort of rides that you can come in and walk in a room that was built for you for that. And they have a range of vibration of floors and heat and cold and wind and spray of water droplets and things like that. You can generate very, very persuasive experience. I don't think consumers will invest that amount in a room to generate that, but I think I do have hope that we will get that in a form of retargeting experiences to different places that we could focus the effort of rendering, or that we could maybe use our other senses to generate prediction, then generate some haptic feedback. For example, there's works that try to generate synchronized haptic feedback in other places, maybe on the wrist while you're touching things, and just use the fact that they're synchronized in time and your expectation to have some haptics to that the brain will combine them might work. And beside this, who knows? Maybe someone will develop a programmable material that could have a shape-changing proxy that, according to what we need, we'll see.
Thanks very much. So I'd like to thank you for quite a marathon session. Such an important topic. Us people, we work in VR. We often can't deal with the haptics because it's just too difficult. But obviously in our everyday life, haptics is critical. Like I'm sitting here and I feel everything around me and so on, but somehow in VR, we don't take that into account as much as we should. But on the other hand, it's really difficult, as you pointed out. So thanks very much. I wish in this system you could hear the applause. You're welcome, and it's been really interesting. So just before we close, I'm just going to announce a couple of things. Thanks again to Dr. Sylvia Pan, who's been behind the scenes making sure everything works. And next week we have Doron on brain control interfaces for virtual reality. That's 1st of June at 4 o'clock, CEST, Madrid, Paris, and so on. And then on the 4th of June, we have another speaker, Mark Gonzalez Franco, also from Microsoft Research, and she's on at 6 o'clock on the 4th of June. So thanks again, Eyal, and I think we finish now. Thank you.
Okay. Bye.